We now look at the impulse momentum theorem. So we define impulse as, write it as a capital I, and that is written as the change in momentum in a collision. So if you have a collision, for example, you have a wall and a ball comes this way, hits the wall and bounces off in this direction. So it has a collision, it has some initial momentum and some final momentum. The change in momentum Pf minus Pi is the impulse. So it's simply the change in momentum in a collision. Now, we know that F equals ma, which we wrote as dp by dt. So the force is a rate of change of momentum, and this is rearranged to give us dp is f dt. Now, if the force during this collision in this little portion of time, as it's going here and it's hitting it and going back, the collision is not instantaneous. It takes a rather short time, but the time is not zero. And this dt or delta t is the time during which the actual collision is taking place. It could be a second, a fraction of a second, a millisecond, but it is a finite period of time. It's not a zero. It's not an instantaneous action. It does take some time. So during that period of time, if the force that the wall exerts on this ball, that's what causes it to be pushed this way. Okay, the ball was going to the right, the wall kicked it to the left, so it moved this way. So the wall exerted a force on the ball, which is here. Now, during the entire period of delta t, if that force is constant, F is constant, then we could simply say that delta P is that whatever that constant force is times the delta T. But if that force is variable, so during that delta T the force is changing, then we can say that the delta P would be the integral of F dt, and we would now need to know the form of this force, the functional form of that force, so that we are able to solve this. Well, we do know delta P. We know the initial velocity and the final velocity and the masses, so we know this thing. Through this impulse momentum theorem, we are interested to find the value of the force. That's the thing we are going to try to find. And this integral would be from the initial to the final points in time, and the initial point in time is when it just touches it, and the final point is when it just leaves it. And the t1 minus t2 is the time during which the two objects are, let's say, in physical contact. Now, to look at this in a little bit more easy way, let's suppose that we have a surface, well, this is a surface, and we have a ball that's falling down. So let's consider the ball to be here and going downwards, and let's consider this to be the time axis. Now, so at this instant of time it's here. At the next instant of time, well, next unit of some time later, it's right here, so it just touches the surface, but it's just barely touched it. Then after some more time, because it was falling down, it would, and let's assume it's like a soccer ball or a tennis ball, something that's somewhat flexible, so it would tend to keep on going lower and sort of get flattened on that surface. The volume would somewhat reduce, the pressure would somewhat increase, and there would be a force acting on it that's going to try to push it upwards or slow it down. Let's assume it still keeps on going and it gets further flattened, well, maybe not so much, but in the next instant of time it's going to be somewhat more flattened, and then it's going to start moving back upwards, and let's assume the same shape as here, and then after that in the next time instant it's again spherical and just touches the surface, and then after that it's back up again. So this is like the collision, it starts squeezing and then it pushes back up again. Now on the same axis, if we draw the force, this is the time, this is the force that the wall is exerting on the ball. So here the force is 0 because it's not in contact, and let's make these lines straight under them. So here the force is still 0 because it just touches it. Now here the force will be somewhat larger, and here it would be still larger. Let's make this somewhat bigger. So the force is here, and here the force would be somewhat larger, and then the force is reduced because it's starting to expand out now. Force is somewhere here, and now it just left it, so the force goes to 0 and remains 0. So the force is going to go up like this, and well, it doesn't have to be symmetric, but it may take a shape of something like this. So the force is variable, and this is the T initial where the collision started, and that's T final where the collision ended. And now if we take the integral of f dt from the initial to the ending time, this would be the delta p. This would be the area under the curve. So it's going to be this whole area. That's going to be the integral. We would be able to solve this if we know the shape of this function, but that is something extremely hard to determine. It can be determined, but it's a rather very rapid process, and we have to have good instruments. However, we could assume that the force stayed, we take that not constant, but we take an average force, we call that F average, and we would assume that the force remains constant for the entire duration at the average value in such a way that the area under this curve is the same as the area under the actual curve. So then the integral of F average dt is the same as the integral of the actual f dt, or in other words, the areas are the same. And in this case, it then becomes sort of, because this is constant, it can be taken out, and the integral of dt is simply the delta t, and so the delta p would be the f average delta t. And now if we know delta t, we can calculate the f average. So we use this equation to, and that's the impulse. So we use this to find the f average through an example. Now, so let's suppose we have a car that's going to the right. We'll take the same numbers as in the book. That's the initial velocity, and that is equal to 15I, so it's going in the I direction. In the book it's going in the negative I direction. I'm just changing that so that we can see both conditions. It goes, hits the wall, which is a strong rigid wall, and the car bounces back with a V final equals to the left, so it's minus 2.6 I meters per second. The mass of the car is 1500 kilograms, and we want to find the force that the wall exerted on the car during this time, and the time we say is 0.150 seconds. So 150 milliseconds or 0.15 seconds. Now we want to find the force. So we say that the impulse equals delta P equals the integral of f dt, which we say is f average delta T, delta P. The delta P is going to be mv final minus mv initial, which is going to be the mass, 1500. And we can write it as mv final minus v initial. So v final is going to be negative of 22.6, and the v initial is plus 15. So it becomes 1517.6. The two speeds actually add up because one is positive, one is negative, and we're taking their difference. So 1500 times this becomes 26,400, and it's kilogram meters per second. And this is going to be equal to f delta t, and therefore the f average is going to be delta p over delta t, which is 26,400 over the time, 0.15 seconds. So this is going to be a negative 1.76 into 10 to the power 5 I, because, well, we can write it's in the I direction. We could put an I here and I here and I here, newtons. So about 2 × 10⁵ newtons is the force that's exerted by the wall on the car, but for a very short time, for 0.15 seconds. Well, it may be enough to damage the car, certainly, because this is a very large force. How big is this force? Well, if you take a 60 kilogram person times 9.8, then the force or the weight of this person becomes 588 newtons. Let's assume it's 600 newtons. That's the weight of one person. So you divide this by 600, so this becomes equal to almost 290 persons. So it's as if on the car you had 290 people jump on the car and jump off after 0.15 seconds. So only for this duration you had 290 people on the car, well, on this direction. So it's not exactly right because the weight is, the people is downwards. This force is to the left, but this gives an idea of the strength of that force. Now we do another, it's not really an example, but something to indicate the effect of the importance of the delta t. So let's consider that you have a table here, and on that table you have a person, and he just jumps down from the table. And you can do that. I mean, it's not such a hard thing. But in this first case, we assume that the person jumps down and he keeps his legs straight. Okay, he does not bend knees. What will happen is that as soon as he hits the ground, because he's almost a rigid structure, he will stop in a very, very short period of time. The delta t is small, and the delta p is going to be mv final minus mv initial. So you have some final velocity, and this would be just after the collision, that's 0. The initial velocity would be the speed with which the person is hitting the ground, and that would be the momentum, and divided by delta t would be the force. And delta t is small, so this force is going to be large. Now, the same person from the same height jumps off once again, but this time as he falls, he bends his knees. Okay, so he's looking this way, so the knees bend. The bending of the knees means that after he touched it, the body kept going down. the knees kept bending, and by the time he stopped completely, some time had taken place. So it was, well, larger than before. Larger than this case. And because that's bigger, when delta t is bigger, the whole force gets smaller. Now, the delta p is the same because you jump from the same height and you hit the ground with the same initial velocity, and the final velocity is 0. But the delta t is bigger, and therefore the force is much smaller. And this smaller force acts for a longer time. So Tf, so the smaller force acts for a longer time. And here we had a bigger force acting for a shorter time. Okay, so the time is short because it just stops quickly. If the time is long, the force is smaller. The area here is the delta p, and the area here is also the delta p, which are both equal. But this is a bearable force, and this may be unbearable. And certainly in this case, it's going to hurt the back really hard. So it's not the delta p that's important, but it's the delta p over the delta t. So we want to increase the time over which we slow down and stop. In other words, we want to reduce the acceleration. So we want that to be small so that the force is small, and that becomes bearable. Now this thing is another example could be that if you take a brick and you throw it vertically up, and then when it falls down you want to catch it, so, and you hold your hand rigid, so when it hits your hand it's going to hurt. So you move your hand slowly with it and slow the brick down. This is used extensively in automobile safety, where the purpose is not to prevent damage to the car, but to prevent damage to the people who are in the car. So the purpose of, or one of the ways, or one of the more important ways, is to increase the delta t, so that in a collision you don't stop suddenly. And for that, one thing that has taken place is that instead of the hard steel bumpers, which used to be common in older cars, bumpers, we now have these plastic bumpers. Okay, so they are crushable and they break, and as they keep breaking, the car keeps slowing down, and it extends the duration of the collision. It increases delta t. Hard steel bumpers would be like jumping here, and plastic bumpers would be like this. So they increase the time of collision. The time is still very short, but it's much bigger than what it was here. So if the time is a millisecond here, it is 10 milliseconds here, while you increase it by 10, you reduce the force by 10 times. Well, that would still not be enough in many cases, so we do something else. Instead of having a strong steel body of the car is crushable. So the front of the car starts crushing when the car hits something in front. So here's the car, and it hits, let's say, a rigid wall. Then first the bumpers will break, that will slow down the car a little bit. Then this part will start crushing and going in, and that will further slow down the car. The rest of the car will keep on moving forward. And then you have the engine. Well, then you'll slow down much faster because it's a big heavy thing. But the car will just sort of break. The whole part will just be completely damaged. But the time it takes from here up to here would be somewhat longer than if you had a very strong rigid body, which would just stop very quickly. And so that increases the duration of collision. Then we have padded dashboard. So if you hit a hard dashboard, then you would stop more quickly, but if the dashboard is padded, well, it takes a tiny bit more time. Then we have seat belts, which also do the same thing, because you lurch forward and then you slow down, so that it extends the delta T, and airbags. So both of these increase the delta T, but another thing that they do is they increase the area of contact, area over which the force is divided. So imagine that in an accident you don't have a seatbelt or airbag and you go and hit the steering wheel. So as you hit the steering wheel, well, it's a hard surface and you would stop in a very short time. But with the airbag, that's a time thing. It will increase the time, but also with the airbag, the whole body will feel the impact rather than only your hands or ribs or whatever hits the steering wheel. So when the force is distributed, then it gets much, it's somewhat more bearable than what it would have been otherwise.